Thank you, Thompson, for the introduction. My name is Ramontsheng, Rapolaki, and can everyone see the slide?
Yes, I can see it.
Okay, thank you. So I'll be talking about wet days and dry spells and the associated moisture transport over Southern Africa. Okay, so this slide here shows the study region, and the map I'm using was adapted from Monday in Washington 2017 and has been modified to include the location of the Botswana High. I'll speak briefly about these features on the next slide because Chris has already mentioned some of them. Southern Africa as a region is agriculturally intensive with large population that rely on rain-fed agriculture. Therefore, understanding the nature or characteristics of rainfall over this region is important for that user group. The objectives of this study were to investigate the spatial distribution of moderate wet days as well as dry spells during the rainy season of Southern Africa, which is defined as DJF, and also to assess the extent to which CMAP6 models can represent dry spells and wet days and what are their associated moisture flux, and also to look at the influence of other circulation features on the spells. I won't waste much time on the slide, just to highlight a few of these circulation features. One of them is the Angola low, which is lower to mid tropospheric cyclonic circulation, which occurs over this region during summer, and it's also the source region of the cloud bands. And we also have the Botswana High, which is a mid-level circulation or a feature, which also occurs during summer. And previous studies, Driver and Racing, have shown that there is a stronger relationship between the Botswana High index and dry spell frequency for several important agricultural regions than exists between ENSO and dry spell frequency. And therefore, a better understanding of this feature can give an additional insight into the climate variability of the region, and also can be a useful tool in seasonal forecasting efforts over Southern Africa. The other important feature is the Mozambique Channel Trough, which we'll talk more about. However, previous studies have also shown the intensification or weakening of the MCT can influence or affect the amount of moisture being transported into Southern Africa. So we've also learned from the previous talk that the diverse topography over Southern Africa also tends to, can influence the spatial distribution and rainfall patterns in the regions. So the key moisture transport pathways in Southern Africa include the southeasterly flow from the Southwest Indian Ocean. There is also the northwesterly flow, as well as the northeasterly flow from the tropical Indian Ocean during the summer months. So these are the data sets used in the study, which chips daily rainfall data for precipitation, era 5 for atmospheric circulation or atmospheric variables, and 5 CMAP6 models. However, moving forward, the number of models would be increased to have a more reasonable and meaningful results. So this is how the wet days and dry spells were identified. A moderate day is defined as any day recording at least 10 millimeters of rainfall and 30 millimeters at most. This criterion was chosen from what is optimal for intensive cropping, because if you look at rainfall values greater than 30 millimeters may lead to reduced crop yield due to waterlogging, soil erosion, and nutrient leaching. Whereas values less than 10 millimeters may resemble a dry spell. A dry spell is defined as any painted recording at most 5 millimeters of rainfall. On this slide, I'm showing the seasonal climatologies over Southern Africa of precipitation. And on the left, it's observations and in models. And this is the difference, so models minus chips. And what we see Generally, in terms of the patterns, you tend to have high rainfall over the Congo Basin, extending eastwards over northern parts of Madagascar, of Mozambique, including over Madagascar. However, the difference in that is the magnitude of, amongst the models and compared to observation is the magnitude of precipitation. And also, if you look at the CNRM, it shows a large amount or high amount of rainfall over the West Coast, which you compared to CHIPS, which you really don't see much of that in other models. So looking at the dry spell frequency over the region calculated between 1981 to 2014 DJF, again, you see high frequency over the West Coast. And there's also this northwest, southeast gradient through southern Angola, over southern Botswana and Namibia, as well as Western Cape, including central parts of South Africa and CHIPS. You see the same pattern or similar pattern in the other models as well. However, the difference in that would be the magnitude. And also, what's noticeable is the low frequency over convective hotspots, the Ramontsheng Mountains here, as well as over Madagascar and the Congo area. So when you see this sort of high, low frequency of dry spells, and also the signature of that drought corridor through the Limpopo Basin. However, it doesn't feature strongly in some of the models. Looking at the moderate days for the same season, you see a more high number of wet days over Congo, as well as northern and eastern Madagascar. And there's also high mean frequencies over the convective hotspots again, or sort of regions of high topography, which would include the Drakensberg mountain regions, downstream Malawi here. And again, low mean frequencies along the West Coast. And again, this disagreement among the 6 model simulations in CHIPS and in models as well. Looking at the moisture flux convergence and divergence, so the positive or the reddish plots will show the divergence, in the blue is the convergence. So, and the other thing I would like to highlight on these slides is in some models, you have these blocks where you don't have data. And this is due to topography, because we are looking at 850 hectopascals. So the topography extends beyond that around this region. So you don't have data in that, and you can't resolve any or get any circulation in that region. And again, if you look along the West Coast, where you have high number of dry spells, which tends to have this divergence, as well as over some of parts over the region of the Botswana High, and also convergence in regions where you have more wet days. And again, this is the differences. So it shows that the magnitude, although the patterns might be more or less the same, the magnitude so varies among the models and in observations. And on the slide, I'm showing the 500 hectopascal geopotential height. And so what we see is this region of high pressure in observations and in model, but then it differs from among the models and also compared to observations, and tends to be stronger in this year NRM as compared to other models. So this is an ongoing study, and I'll be looking at other features as I move forward. So there is no conclusion, but a summary of the results so far. And so we noticed that there's an agreement among CMF6 models and chips of mean DJF distribution of price per frequency across Sub-Saharan Africa. However, there's a disagreement in the number of moderate wet days among the models and in observations in those regions, which will include the Congo Basin, Drangasberg Mountain, Maluti Mountains, and Madagascar. So moisture flux convergence divergence pattern seems to match regions of high or number of wet and dry spells respectively. There's also a little agreement among CMF6 and observation in the magnitude of the Botswana high. And this strong mid-level Botswana high is sort of, if you look at the CRNM, you look at the dry spells as well as its intensity. There's also, it's consistent. There's also a consistency. And also the model seems to have trouble adequately representing the Eastern escarpment, particularly near the Maluti Mountains and the Drangasberg, Southern Drangasberg, where you have those blocky rectangles, and there's no data there. So that could be another thing to look at. Thank you.